Hey everyone, today we're going to talk about section 6.2. That is the analysis of initial value problem solvers. So if you can recall from last class, we talked about Eulers' method. The Eulers' method was a method for solving initial value problems. And with one of our last examples, we looked at how changes in H affected our error. So we created tables of error terms associated with our approximations and the actual solution. Then we halved the value of H. I think it was from 0.2 to 0.1. And then we saw that we got half of the error as a result. So the motivation for this section is this always true? Is this generally true? If we just keep halving the value of H, will we get half as much error each time? So before we start, we need to identify two definitions here. So first is called the global truncation error. The global truncation error is simply the difference between the ODE solver, like Eulers' method, and the actual solution of the initial value problem after I steps. So when we were doing our tables, that's the error term that we are calculating. We were calculating the global truncation error at each of the I steps. Okay. Another type of error is called the local truncation error, and this is the difference in our approximation to the actual curve using one step of the method. So it solves the initial value problem, y prime equals f, y of ti equals wi, in the interval ti to ti plus 1. That's just one step, that ti to ti plus 1. So the new global truncation error on the next step is the combination of the amplified global truncation error from the previous step plus this new local truncation error. So it's tough to find what the local truncation error is outright normally, but we know that the global error on the next step is equivalent to the previous global error plus some amplified, or the previous amplified global truncation error plus this new local truncation error. Okay. So, it can be shown that the overall global truncation error at the ith step is bounded by the following expression here. So GI will represent the global truncation error on the ith step. It's less than or equal to this weird formula over there. But we won't be concerned with what C and L are. But note that the global truncation error is proportional to h to the k power. So when h gets lower and lower, this term in front gets lower and lower. But you can see that there's this exponential term in there. There's this exponential term in there here. So let's look at an example, and we'll come back and see why this term, what happens with this error, okay? So let's look at this example here. So we're going to use MATLAB to solve the initial value problem to approximate the solution at y of 0, and we'll use three different h values, so 10 to the negative 3, 10 to the negative 4, and 10 to the negative 5. So here we have our derivative function, negative 4t to the third, y squared. Our initial condition is at x is negative 10. We get 1 over 10,001. And our interval on t is negative 10 to 0. So we're looking at the solution at the very end of that interval. Also note that the solution, the exact solution, can be found by doing separation of variables here. We can just separate the variables and anti-differentiate. We'll end up getting 1 over t to the fourth plus 1. So we want to compare the global truncation errors for each value of h here. Okay. All right, so let's implement this in MATLAB. My Euler function will take on h, a, b, and y naught. That's up to you to do that, so I won't show you explicitly what the code is. So we need to define our first h. Let's say h is 10 to the negative 3. And a is negative 10. and B is 0. And why not is the value of the initial condition, so 1 over 10,001, right? So here you can see my values have been defined in my workspace, so we can run Euler. Okay. So I've also plotted this, so you can see here my answer is the global truncation error. So here is the error at the very last step, approximating y of 0. So you can see when h is 10 to the negative 3, that's pretty low. The error is very, very large. Recall that the solution, the exact solution, is 1 over t to the 4th plus 1. So when t is 0, the solution is 1. So here we have an error of 0.8789. That's a humongous error for such a small h. You can see here the plot of the function, so from negative 10 to 0. Gets us at about 0.12, right? So we are far, far below our solution there, okay? Let me put my hold on so we can compare the graphs. Now, let's change our h. h is now 10 to the negative 4. And rerun our Euler method. All right, so here we see that the error is 0.4223. That's about, that's a better improvement. Pretty, not very good because it's still 0.4. It's a pretty big error. Let's see about our graph. So you can see here, here was our old one, right? It was at 0.12. Here is our new approximation to the solution curve. That's roughly 0.6, right? Just under 0.6, 0.57 or so. So you can see the error did decrease when we decreased h. Now let's change it to 5. We'll rerun it. All right, so now our error is significantly lower when we are at h equals 10 to the negative 5. And here's a graph. So here's our first one is blue, second one is red, now our third one is approaching that exact solution there. So it does seem that Euler's method does produce lower error every time we lower the h value. However, the catch for that is that there's a lot more computation, right? A lot more computation involved. Watch when I do this for h equal to 10 to the negative 6. Let's see how long it takes to calculate. It's taking a pretty long time, right? So there's a lot more computation in order to get this accuracy, right? 0.0073, so we're even better. But that's still off by 3, about 10 to the negative 2. It's getting better. So that's our purple curve there. Okay? So we do see that Euler's method increase accuracy as we decrease the step size, but it requires more and more computation. So this begs the question, is there a better way? Can we get better results in less computation? And the answer is, of course, yes. There is a better method for solving these initial value problems numerically with a second method. Okay? So the second method, they call it the explicit trapezoid method in your book. But it's also called the improved Euler's method. Okay, so here it is. You can see our initial condition is the same as our initial approximation, and here is the formula that will iterate to the next solution, okay, the next approximate solution. So it looks a little jumbled, right? If we kind of just disregard this second piece after the plus sign, that's pretty much Newton's method, with h divided by 2. We have this other wacky term right here. So let's see a derivation for this. All right, so here's how we're going to derive the explicit trapezoid method or improved Eulers method. So let's start with our graph. All right, so here is our t-axis, here's y-axis. Say we have this function here. Okay, so this is y of t. All right. So recall with Euler's method, let's say we have our t0 here, and t1, let's say is right there. Okay. So it's known, there's a known point on the function, our initial condition, right? So we have our initial condition here. That was y naught, aka w naught also, right? W naught. Initial condition, w naught and y naught are the same, right? From here, right? So we know that point. What Euler's method did was used a tangent line to approximate the location of y1, right? So if with Euler's method, we used this tangent line here, traveled over a distance of h units, right? To get this next, extend this a little bit. So to get this approximation, W1, that approximated the y coordinate of the curve, which was y1. Right? And then we had it, like if we had a T2 over here, we would do it again. We would use the slope of the curve itself to generate another tangent line. Let's try to make it parallel here. Another tangent line to approximate at T2, right? So what improved Euler's method does is it uses the average of these two slopes. It uses the average of those two slopes. So if you can imagine like a dotted line here that kind of splits them in half, that would be the average. That would be the line that has the average slope of both of them. Okay? So again, we take the average of these two slopes, and we're going to apply it to this point instead of the slope of this tangent line. Okay? So we can see, try to make it parallel, if we apply this slope through this point, we see that our approximation with improved Euler's method, that would be our W1, would be super duper close to Y1. So you can see we can get a better approximation if we utilize this method. Okay? So let's see how that formula is created here. Well, we know if we call the slope, let's say the slope of our initial tangent line, let's call that S1 for slope 1. And then the slope of our second one was S2. Therefore, the slope of our average would just be, say, average slope would be S1 plus S2 over 2. All right? So let's just get some preliminaries here. So we know that this point right here is T1, comma W1, right? Well, you know that T1, comma W1 actually can be rewritten. What is T1? Well, T1, W1 is equivalent to, well, we know that this distance here is h, right? So T1 is actually T naught plus h, right? T1 is just T naught plus h. All right? And W1 was found from doing Eulers' method, right? Eulers' method was used here, and recall Eulers' method. So W1 was equivalent to W0 plus H times F. Remember, F is our derivative at T naught W0. Okay. All right, so how do we get the slope? So if we're going to use the slope of this line here, instead we're just going to use kind of an Eulers method approximation, but instead of using the slope of the tangent line, we're going to use this average slope that we're going to calculate from the average of these two guys, right? So remember our slope 1, slope 1 is equivalent to the slope of the tangent line at W0, which was f of T naught W0. And S2 is the slope of the tangent line at this point. So that would be f of T1 W1. Or f of T1 W1 is actually this point right here. That would be f of T naught plus H, comma, W naught plus HF T naught W naught. So our improved W1 will be equal to W naught plus H times the average of these two slopes. So f of T naught W naught plus f of T naught plus H, comma, W naught plus H, f T naught W naught. All over 2, the average of those two slopes. Okay? All right, so that's how we get our improved W1. Therefore, if we generalize this, Wi plus 1 is equal to the previous one, Wi plus, I'm going to pull that 2 out, H over 2 times f of the previous slope plus f of new slope, which can be gathered this way, Ti. Okay, so that gives us exactly that formula right there. Okay. So a little more complicated when we introduce that average slope there, but nothing the computer can't handle, right? We can always just calculate this. The Ti values are known, the Wi values are known if we're looking for Wi plus 1. So this is absolutely doable. It's explicit, which means it doesn't depend on any of the next terms, okay? All right, so let's look at an example. Example 2 says, given the initial value problem below with h equal to 0.1, and we want to find the analytic solution to the initial value problem, and then find the solution at 1.3. Then we're going to use Eulers' method to approximate the solution, and use improved Eulers' method to approximate the solution, and then compare the errors. All right, so let's take a look. So first we need to find the analytic solution to this problem right here. And we can do that one of two ways. We know that y1 is 1. That's our initial condition. So we could use separation of variables here. We could actually multiply by the integrating factor It doesn't really matter. I'm going to just use the integrating factor way to do the problem. So the integrating factor, recall, is e to the negative integral g of t dt. So that would be, in this case, our g of t is the function, the function of t that's connected to y here. So it would be e to the negative integral of t dt. Okay. Which is e to the negative 1/2 t squared. All right, so multiplying each side by the integrating factor gives us half t squared y prime equals t e to the negative 1/2 t squared y. All right, so I'm going to move this term over. Equals 0 this time. So we don't have a second function. It's usually equal to some function here, but we can get this to be homogeneous. So remember the trick with the integrating factor. The reason why this works is because we can write this as a derivative. So that would be the derivative of y times the integrating factor. It's always the case. Okay. Integrating both sides gives us y times e to the negative 1/2 t squared equals, again, we're integrating with respect to t. So the integral of 0 is some constant, right? So it's just constant, because the derivative of a constant is 0. And then we divide both sides by e to the negative 1/2 t squared. So y is equal to c times e to the positive 1/2 t squared. Again, dividing by e to the negative 1/2 t squared is the same as multiplying by e to the positive 1/2 t squared. So now let's use our initial condition in order to find the c value here. Okay, so using y1 equals 1, we can find that. So y is 1 when t is 1. E to the 1/2. So dividing by e to the 1/2 on both sides gives 1 over e to the 1/2 equals c, or c is e to the negative 1/2. So again, just subbing in the values for y and t gives us this. Divide by e to the 1/2 on both sides. 1 over e to the 1/2 is the same thing as e to the negative 1/2. Therefore, our analytic solution is y equals e to the negative 1/2 times e to the 1/2 t squared, which actually can be rewritten. If we multiply with like bases, we add the exponent. So this is actually e to the 1/2 t squared minus 1/2. So there's our analytic solution. Y of 1.3 is equal to, just plugging in 1.3 there, looks like approximately 1.4119892. Okay. Now we want to use Eulers' method to approximate this solution, see how good Eulers' method approximates this, and then look at the global truncation error for our last step. Okay. would be. So recall Euler's method. It says our initial approximation, and then our next approximation is previous plus h times f of ti. Again, where f is equal to y prime. Okay. All right. So let's do it. So let's say I is 0. Now, how many iterations are we going to need to do? Well, it depends on h and the interval that we're dealing with, right? So we're going from, actually, let's change this to 1. So let's look in 1 to 1.3. So our initial condition, it should match to the initial value here. So 1 to 1.3. So if we look at our axis, 1 to 1.3. And if h is 0.1, so we would get to 1.1, 1.2, and 1.3. All right? So here are our t values. And we're looking for our w values, right? W values here. Well, we know at 1, this guy is 1. Okay. So we would need to do 1, 2. So the first iteration finds W1 for us. The second will find W2. The third will find W3. Okay. Here are our W's. We'll also need to calculate our I's and then our errors. Okay. So it'd be global, right? Global errors. So let's do that. So W1 would be W naught plus H times F of T naught W. Okay. So in this case, it would be W naught plus H times, well, what is F? F is T times Y, right? So this would be T naught times W naught. So plugging in those values, W naught is 1, H is 0.1, T naught is 1, times W naught is 1. So that gives us 1.1. So our W value is also, W1 is 1.1. Let's calculate our exact solution. So e to the 1/2 times 1 minus 1/2 is 1. Excuse me. So that would be T naught. T1 would be 1. So I'm getting 1.11071. So we just round to that many decimal places. So it looks like our global error is that. Now for W2. W2, we need W1, 1.1, plus H times the previous T times the previous W. So let's see what we get there. .1331. Let's calculate the y value at 1.2. So this would be 1.246077 approximately. Excuse me, this is incorrect. This is 1.221. So I'm getting an error of 0.025 0.77. So again, global truncation error. It's magnifying this error, right? And then last one, W3 is going to be previous W plus H times the previous T, which would be 1.2, times the previous W, 1.2. Getting 1.36752. Okay. Now, if we check the exact solution, we found the exact solution at 1.3, which was 1.4119892. So our error is 0.04446 992 approximately. Okay. So that's Eulers' method. You can see here we're looking for the global truncation error at the last iteration. So by the time we get to the solution, we are going to be this much off, right? This much off, which is a pretty not too great approximation. Okay, not bad, but not great. All right. So now let's try improved Eulers' method and see how that goes. Okay. All right. So the formula for that. So W naught is Y naught. Wi plus 1 equals Wi plus H over 2 times F of Ti Wi plus F of Ti plus H, comma, Wi plus H times F of Ti Wi. And that's just coming from there. All right, so carefully, there's a lot more stuff going on, especially in this little area over here. Okay, so let's remind ourselves of our T's. And then our W's will be here. Okay, so W1. Okay. What's that going to be? Well, here would be W naught. What's W naught is our initial condition. It's 1 plus H over 2 times F of Ti Wi. Well, F is just t times y. So this would be t0 plus t0 times y0, w0. So what's t0? That would be 1 times w0, which is 1 as well, plus f of t0 plus h. Well, that would be t0 plus 0.1, which is 1 plus 0.1, times this guy for y. So w naught plus h times f of t naught w naught, which would be 1 times 1. Okay. Note that we already have these solved for, but we can solve for them again. E1 plus 0.1 divided by 2 is 0.05 times 1 plus, let's see what we get here, 1.1 times, this is 1.1 as well. So 1.21. Oh, that's just the Euler method solution. Calculating this, we will get 1.1105. Okay. So you can see it's a little larger than the Euler's method, but closer to the actual solution, right? Much closer to the actual solution. All right, W2, what would W2 be? What's the previous W plus h over 2 times the derivative function evaluated at the previous t and w. Okay, so here we would be at t1. T1 is 1.1 times w1, which is 1.1105, plus, now here it's f of the previous t plus h, right? So here would be a t1, its index is 2. So t1, which is 1.1, plus h is actually 1.2. Times, now this value here. So the previous w plus h times t1 w1. T1 times w1 from our formula. T1 times W1. Oh, or H is 0.1. Alright, so just be careful here. Alright, let's put all that in. This is 1.2455368 approximately. Okay. Alright, one more. W3 equals previous W plus H over 2 times, need to evaluate at the previous T and W, so the previous T would be 1.2, previous W is 1.2455368 plus the derivative evaluated at the next t value, which would be 1.3, times previous w plus h times the function evaluated at the previous t, so that would be previous t would be 1.2 times the previous w and brackets on that. Okay. So let's see what that is. Calculating that gives 1.410944 approximate. Okay. So let's make a table. And so I 0, 1, 2, 3. Our approximations are 1.1105, 1.2455368, 1.410944. The exact values we can get just from our other table: 1.11071, 1.246077, 1.4119, 8992. So just filling those in. Again, here are our approximations. W0 was the initial condition, which is 1. And those values, here we got those from our last table. So let's calculate our errors. So error at the first step is always 0. Here we get negative 2.1 times 10 to the negative 4. We get negative 5.402 times 10 to the negative 4. And here I'm getting negative 0.001. No negatives involved. Absolute value values. Okay. Of 4. Okay. So our global truncation error, you can see it increased each time. Of course, it's 0 because the initial condition is equal to the function. But it increased each time, right? Increased a little bit here, and then, sorry. Global truncation error is 0.001. So if you compare that value, comparing the two, you can see that it is many times smaller than the Eulers method alone. Okay. So you can see that the our improved Eulers method, or the trapezoidal method, is a more accurate method, but it takes a heck of a lot more computation. In fact, it takes 2 more function evaluations than the Euler method, right? Lots more computation involved in this one than with this one, okay? So you should be able to do the homework assignments for this chapter now, okay?